Welcome back to the deep dive. Today we are strapping in for a pretty epic journey. We're looking at timescales that make human history seem like, well, barely a blink.
That's right.
We're doing a deep dive into the changing Earth geology, basically. We're talking about the planet's fundamental structure, the massive slow motion processes that have shaped, everything around us.
The only home we've got.
Exactly. So think of this as your quick guide, your shortcut maybe, to getting really informed about the history that's, well, literally written in stone. Okay, so our mission today, as we go through the material, is to hit 4 key areas. We'll start with the basics, the building blocks, that's rock composition.
Right.
Then we jump into the dynamics, the rock cycle itself.
Yeah.
After that, we'll look at how rocks hold secrets, ancient ones in fossils.
The history.
Yeah, the history part. And finally, we'll look at the forces shaping things right now, weathering and erosion, the Earth's current agents of change.
And setting the stage for all of that, we really have to begin right at the foundation. We call it the lithosphere.
The lithosphere.
Okay, it's basically the planet's rigid outer shell, the bedrock of our whole conversation, you could say.
Nice one.
And the crucial thing to grasp right away is that all rocks, every cliff, every pebble, every grain of sand, they're all made up of minerals. Organized structures of minerals.
Okay.
Understanding that, the lithosphere and its minerals, that's kind of the key to unlocking how the planet changes on a bigger scale.
Right, so let's get down to that level then. The lithosphere is the big layer, minerals are the tiny bits inside.
Pretty much.
So imagine a geologist out in the field picks up some random rock. How do they even start? How do they figure out what it is they're holding? It's like detective work, isn't it?
Absolutely. It's a process.
Yeah.
Mineral identification relies on looking at a specific set of physical properties you can observe.
Like what?
Well, there's a kind of checklist they run through. They look at hardness. You might have heard of the Mohs scale.
Vaguely, yeah.
Then there's cleavage, which is just how a mineral breaks along flat surfaces. And luster, how shiny it is, basically how light bounces off it. But maybe the most interesting one, and sometimes counterintuitive, is the streak.
Streak? What's that?
It's the color of the mineral's powder. You find it by rubbing the mineral against a little unglazed porcelain plate.
Why powder?
Well, think about gold versus pyrite, fool's gold.
Right, they look almost the same.
Exactly, same brassy metallic look. But rub them on a streak plate. Gold leaves a gold streak, pyrite leaves this dark, greenish-black streak.
So the powder color is different.
Totally different, that little test. It's often the deciding factor, a really practical key identifier in the field.
That's actually super helpful. Okay, so we know what the building blocks are. Now, how do they move? Because rocks aren't just sitting there forever, are they?
Not at all. They're constantly changing.
Which brings us nicely from composition to the dynamics, right? The rock cycle, you mentioned 3 lives of a rock.
Yeah, the rock cycle. It's like geology's ultimate recycling program. It never really stops. You basically have 3 main categories: igneous, sedimentary, and metamorphic.
Okay.
Igneous rocks, they're born from heat. They form when molten rock magma underground or lava on the surface cools down and solidifies.
Got it.
Fire rocks. Sedimentary rocks are usually about layers. Bits of other rocks or shells, organic stuff, even minerals that precipitate out of water.
Yeah.
All that gets compacted and cemented together over time.
Right, like sandstone or shale.
Exactly.
And the third type, metamorphic.
Metamorphic rocks. They're the transformers. What's really distinct is that they form from other rocks.
From igneous or sedimentary?
Yeah, or even from other metamorphic rocks. They get changed deep underground usually by intense heat and huge pressure, but without fully melting. They get baked and squeezed into something totally new.
Okay, interesting. Let's focus back on those igneous ones for a sec, the fire rocks. There's this distinction you hear about extrusive and intrusive. They both come from molten stuff, so what's the difference? How can you tell?
It really comes down to where they cooled, which tells you how fast they cooled. Extrusive igneous rocks, think basalt, maybe obsidian they form on the surface, like after a volcano erupts.
So they cool fast, exposed to air or water?
Super fast, geologically speaking. Intrusive igneous rocks, like granite, they form deep down, insulated by all the rock around them. So they cool really, really slowly. Millions of years sometimes.
Okay, and that difference in cooling speed, that affects how the rock actually looks, right? The structure.
Precisely. And this is a crucial connection. The crystal size in the rock depends directly on that cooling rate.
Okay.
Slow cooling underground gives atoms lots of time to arrange themselves into large, orderly structures. That means big, visible crystals. Think of the large interlocking bits you see in granite. That's quartz, feldspar.
Right, you can actually see the different minerals.
Exactly. But fast cooling on the surface, it results in tiny, fine-grained crystals. Sometimes so fast there are basically no crystals at all, like the glassy texture of obsidian.
Is that like a hard and fast rule? Or are there exceptions? Like, could you get big crystals from fast cooling somehow?
It's extremely reliable. That relationship, crystal size, tells you cooling rate is fundamental. It's how geologists identify specific igneous rocks. But more than that, it tells us about the conditions deep inside the Earth or during an eruption long ago.
So looking at the crystals tells you if it popped out of a volcano or just sat miles deep.
In essence, yes. It gives us this amazing window into the heat and pressure, the energy of ancient Earth processes. So the whole rock cycle shows how these types are constantly changing, one into another. Igneous rock erodes into sediment, becomes sedimentary rock, gets buried, becomes metamorphic, maybe melts, becomes igneous again.
A continuous loop.
Yeah. And understanding this cycle, and especially those layers, the stratification in sedimentary rocks is vital. It reveals changes to the Earth over vast stretches of time. They really are like pages in Earth's history book.
That's a perfect segue because we move from rocks as just structure to rocks as keepers of history, which brings us to paleontologists and fossils.
Right, paleontologists are the historians of ancient life, and fossils are their primary sources. We often think of, bones and shells, body fossils.
Ludosaurs.
Yeah, but there are also trace fossils, things like footprints, burrows, even fossilized droppings, coprolites. Yeah. They tell us about behavior, not just shape.
So how does something actually become a fossil? How does organic stuff last long enough to turn into rock? It seems incredible.
It is incredible. The most common way is a process called permineralization.
Permineralization, okay.
For it to happen, an organism usually needs to be buried really quickly after death.
Yeah.
That stops it from decaying or getting eaten.
Right, gets it out of the way.
Then groundwater, which is often full of dissolved minerals like silica or calcite, seeps into the buried remains. It gets into all the tiny pores, the cells. And those dissolved minerals start to crystallize inside the original structure. Sometimes they even replace the organic material molecule by molecule. It basically creates a perfect mineral copy, a stone replica.
Wow, like a microscopic 3D printing job by nature.
That's a good way to think about it, a very, very slow printing job.
Okay, but this raises a really key point, connecting back to the rock cycle. Why do we almost always find fossils in sedimentary rocks? Why not in igneous rocks?
Well, the short answer, fire and heat. Remember, igneous rocks form from molten material hundreds, even over 1,000 degrees Celsius. Any organic matter, any bone or shell would just be instantly incinerated, vaporized.
No chance of survival.
None. Sedimentary rocks, though, they form from layers piling up and compacting, usually in water, at much, much lower temperatures. That gives the slow, gentle process of permineralization a chance to happen.
So it's a preservation bias. Only things that die in the right place, get buried quickly in sediment, have a shot at becoming fossils.
Exactly. It means the fossil record, amazing as it is, only captures a tiny, tiny fraction of all the life that's ever existed.
Okay, so the sedimentary layers are like the library shelves. How do paleontologists figure out how old a specific fossil, a specific book on the shelf actually is?
Well, the layers themselves give us the first clue. We use relative dating, mainly the law of superposition. Basically, unless the layers have been overturned by, tectonic forces, the oldest layers are at the bottom and the youngest are at the top.
So if fossil A is in a lower layer than fossil B, fossil A is older.
Generally, yes. That gives you the sequence. But to get an actual age in years, an absolute age, we need something more.
Like carbon dating.
Carbon dating works for relatively young organic material, but for really old fossils, we often rely on radiometric dating of certain types of igneous rocks found near the fossil layers.
Using those radioactive elements that decay at a known rate.
Precisely. Elements trapped in crystals when the igneous rock formed. By measuring the decay products, we can calculate when that rock solidified, giving us a date marker for the nearby fossil layers. It connects the fossil story back to the geological clock.
That's amazing that a layer of rock can tell us so much millions of years later. But okay, those same layers, they don't last forever either, do they? They're constantly being erased.
Right. Nothing is permanent in geology.
So let's shift to the forces breaking things down now, weathering and erosion.
Yeah, these are the active processes constantly reshaping the surface. Weathering is the breakdown of rock, right where it sits. It can be physical, like ice wedging cracks apart, or chemical, like acid-dissolving minerals.
Okay, breakdown.
And erosion.
Erosion is the movement of that broken down stuff. We call it sediment once it starts moving. Wind, water, ice, gravity, they all carry sediment away. Eventually, it gets deposited somewhere else, maybe starting a new sedimentary layer. The cycle continues.
And while some of this is just nature doing its thing, human activity can really speed things up, can't it? Like acid rain. How does that impact rocks and maybe our cities?
Acid rain is a big accelerator of chemical weathering. It forms when pollutants, mostly sulfur dioxide and nitrogen oxides from burning fossil fuels, mix with water in the atmosphere.
Right.
This makes the rain acidic, and it's particularly corrosive to certain rocks, especially those containing calcium carbonate. Think limestone, marble, common building stones.
So it eats away at buildings and statues. Exactly. You see it on old stone buildings, carvings getting blurred, details lost. It significantly speeds up decay that would naturally take centuries, compressing it into decades. It affects natural rock formations too, of course.
And we see the results of natural weathering and erosion everywhere. Huge landscapes carved out over millennia. The sources mention some Australian examples.
Oh, definitely. A classic example is Uluru, or Ayers Rock, that massive, smooth dome shape. It's largely down to chemical weathering and something called exfoliation or onion skin weathering.
Onion skin.
Yeah, imagine deep underground, huge pressure. Then, over millions of years, erosion removes the rock on top. The pressure lessens, the rock underneath expands slightly, and the outer layers crack and peel off like layers of an onion. That creates those smooth, rounded forms.
Incredible. It takes unimaginable amounts of time.
Geological time, yes.
Yeah.
But that brings us right up against modern environmental issues, where human timescales crash into geological ones, like deforestation and soil erosion. That happens fast.
What's the connection there? How does cutting down trees cause soil to wash away?
Well, think about what a forest does. The trees, the undergrowth, their roots create this dense network holding the soil together. The canopy intercepts rain.
Right.
Remove that cover. The roots die. The soil is exposed. When heavy rain hits, there's nothing to hold the topsoil. It just gets washed away, mobilized really quickly.
Especially on hillsides.
Especially on slopes, yeah. You get massive soil loss,
Yep.
which is terrible for agriculture, clogs up rivers with sediment, ruins ecosystems. It's a huge problem driven by land use change.
So, if we know this happens, what can be done? What are the practical ways to stop or slow down that kind of rapid erosion?
Well, the solutions come from understanding how water flows and how plants work. The most obvious is reforestation, planting trees and vegetation again to rebuild that root structure.
Makes sense. What else?
There are also specific farming techniques, things like contour plowing.
Plowing along the curves of the land.
Exactly. Instead of plowing straight up and down a hill, which creates channels for water to rush down, you plow parallel to the contours. Each furrow acts like a tiny dam, slowing the water down, letting it soak in.
Clever.
And terracing on steeper slopes, building flat steps into the hillside. Same idea. Break up the slope, slow the water flow. It's all about managing water and keeping the soil in place. So as we kind of wrap this up, it's really important to see how interconnected these four areas are. You start with the composition, the minerals.
The building blocks.
Right. Then the rock cycle shows how they transform endlessly. Those transformations, especially sedimentation, trap evidence of past life, the fossils.
The history book.
And then weathering and erosion are the forces constantly rewriting that book, breaking things down, moving them around, starting the cycle over. It's one continuous story. And knowing the basics lets you kind of read that story in the landscape.
It's an incredible narrative, and thinking about those timescales, it's pretty mind-blowing. You have the rock cycle operating over millions, hundreds of millions of years, granite forming slowly deep down. Deep time.
Yeah, deep time. And then you contrast that with things like acid rain damaging statues in 50 years or deforestation stripping soil in a single rainy season. It really makes you think, if those ancient layers tell the story of past life, what story are we writing right now in the Earth's layers with these accelerated changes? What will future geologists read in the strata we're creating?
That's a profound question.
Something to definitely mull over. Okay, that's all the time we have for this deep dive into the changing Earth. We hope this gives you a new lens to see the ground beneath your feet, not just as dirt, but as this ancient dynamic record. Go out and explore it.